Hello, this is my English speaking practice and I'm working on coding problems. I have to solve two problems. Today for Saturday, so it's yesterday. So let's go. Some root to leaf numbers. You are given the root of binary tree containing digits from 0 to 9 only. Each root to leaf path in the tree represents a number. For example, the root to leaf path 1, 2, 3 represents the number 123. Return the total sum of all root to leaf numbers. Test cases are generated so that the answer will fit in a 32-bit integer. A leaf node is a node with no children. Okay? Okay, so in this case, the root node is 1 and it have left child and right child, and its number is 2 and 3. So this path represents 12 and this path represents 13. So the total is 25. So we have to return 25. In this case, 419, 95, and 491 and 40. So the answer is 1026. Okay, makes sense. Makes sense. Yep. Yeah. It's easy to understand and I come up with the solution. We traverse the tree, and when we reach the leaf node, we can fix the number because that's the final digit for the path. So in this case 4, 9, and 5. So we can fix the number 495. And we just sum up them. Okay, so not difficult. Let me see the let me implement this. If S works for this problem, we can going deeper and deeper, and so it takes node. Okay, let me remove the optional and the node and current value. It's int. We can accumulate the number, the value, right? If first, let's see the case when it have no children. It's leaf node. So node left is none, and node right is none. So the node is leaf. So we can fix the value at the path, right? Yep. But I'm thinking about we should return the total value, or just append the answer to the global list. How about return the value? It would be like current value plus node bar. And if there is left child, we cannot fix the value, so we have to call DFS and pass the left node, and the current value would be times 10 plus node value, because it's we have to build the value, so we have to multiply 10. And this function should return the value after all, so this works. Okay, so the result is 0, and we update the result by calling left and right child. Yep. And for this, returns 495 and 491. And for this should return 40. No. No. This is correct, but when current value should be multiplied by 10 at this time, and when we I'm not sure, when we call next function, we have to multiply 10. Yeah, because the current value is expected to expected to be divisible by 10. Yeah, node value is single digit, and current value would be divisible by 10. So at this time, current value would be divisible by 100, and when calling next function, we multiply node value time by 10 and return result. DFS and root 0. Yeah, seems good. And the minimum number of nodes is 1, so I think this function cover it. Yeah, if there is only root node, the root node is also leaf node, so we can return 0 plus node itself, so it works. And is there any cases? No. And node, yeah, node must exist. So yeah, seems good. Let's go. Great, beat 100%. Okay, and this case, should I review my English? I'm not sure. This case is DFS, so let me see the previous or similar. Let me see the similar cases, and because it should have similar vocabularies. So when we call the next function, we do the same for the right side. Hmm. This is not BFS. Go deeper. Do the same. Go deeper into the left subtree if it exists. Let's use DFS here. We will keep track of the depths as we go down. Other current nodes pass. Okay. We need to go deeper. Okay. So this case, yep. If it's leaf node, we can fix the number for the path, right? So this case, if there is left child, we go deeper and current value ten times. Difficult to explain. Yeah. There must be next digit for this path. That's why we times 10 times is the times verb. We times 10 to current value. We multiply. We times 10 times. We multiply. Okay, multiply. if there is left child, this is not good. Current value plus node by 10, and we next value. There must be next digit for this path, so we multiply current value by 10. If there is left child, we do the same for right side. If this node is a leaf, that means we've reached the end of the path, so we can finalize the number formed along this path. Otherwise, there are still digits to explore. Before we go deeper, we shift the current value to left by 1 digit, which means multiplying by 10, then add the current node's value. If there is a left child, we go down that branch. Same thing for right child. There is still digit to explore. Before we go deeper, we shift the current value to the left by 1 digit, which means multiplying by 10. Then add the current node value. Okay, not bad. Anyway, this is the last problem for today. Clone graph. Given a reference of a node in a connected and directed graph, return a deep copy of the graph. Each node in the graph contains a value and a list of its neighbors, like this. Test case format. For simplicity, each node's value is the same as the node index, one indexed. For example, the first node with value 1, the second node with value 2, and so on. The graph is represented in the test case using an agency list. An agency list is a collection of an ordered list used to represent a finite graph. Each list describes the set of neighbors of a node in the graph. The given node will always be first node with value 1. You must return the copy of the given node as a reference to the cloned graph. Sorry. Deep copy. Yeah, deep copy. Huh? So there is an original graph. You cannot return the same graph. This looks like a clone. The nodes are new. Graph looks the same. The nodes were cloned, but the graph is messed up. Doesn't have same connections. I see. Is this difficult? I think this is the implementation problem. So we get a node and it has neighbors. It has neighbors. Yep. What? Can I start to code it? I don't know what is the problem. So we have to clone. We have to create a new node. But the argument is a node. So yeah, we have to. You must return the copy of the given node as a reference to the cloned graph. Okay. So this cloned node var is node var neighbors. Yeah, we initialize the cloned node without any neighbors, because we have to create neighbors for each, so we can neighbors and we get the node. Neighbors is node, right? Yeah. cloned neighbor is like create and neighbors append cloned neighbor, and we've created new neighbors. That is not copy, that is created. Yeah, so cloned neighbors is neighbors, and we return cloned. But there is one problem, cause yep, the 1 have 2 and 4, so at this time 2 and 4 is created. So maybe we have to memorize it, and the number of nodes in the graph is in range 0 to 100, so we can use array, and yep, if memos, wait, edx int we return it. That means yeah, if the new node with index I is already created, we don't recreate it, we just reuse it, okay? And otherwise we clone the node, and for neighbors we need to iterate through the original neighbors, and we call the create function recursively, and yeah, we don't care if the node n is already created or not at this point, but yeah, this function cover it, so we just call the create function and get the cloned neighbor node and append to the neighbors, and yeah, and finally we just before return the new node, we update memos, and we get the index, so yeah, this node is stored at the index I, right? And that's it. And node might be none, so we have to handle edge case. We just return none, and yeah, the number of nodes in the graph is in the range 0 to 100, and this is one indexed. Yeah, node value is same as the node index and one index, so the index ranges from 1 to 100. Yeah, and return create node. That's it. Let me see. Runtime error. Okay. Yeah. The first one is index 1. Let me see. Oh, I see. Oh, I see. Node neighbors and okay, and dot value. Yeah. My mistake. Maximum recursion depth exceeded. Okay. I forget something. I don't know. I have no idea, but around here, calling create function. I see. So we have to there is a cycle, so there is a cycle, so we have to keep track of the visited And if oh wait. Oh, I see. I I noticed I noticed the I realize the difficulty of this problem. Mm. Mm. Yeah, the DFS is not good. So I want to quit the recursive function. I want to use BFS. I will clone the node one by one. Okay, so after we create a new node, we will call the next function. Okay, so the first case is like cloned is node value. Okay, and here we declare the queue. Okay, I don't know how I use this library, this data structure for the first time. No, not for the first time, but yeah, I forget how I use this, but Q is first in first out data structure, so let's initialize the Q. Node neighbors, we get neighbors and put node. Okay, and as long as Q is not empty, I think this is good. We can get remove and return an item from the queue. Yeah, seems good. Head, we can head, and this is original. So we have to oh wait, how to keep track of the oh, this problem is difficult. We initialize 1 and we want to create 2 and 4, and when we create 2, want to create 1 and 3. So when we create we can create the first step is to create node 2, okay? But node 2 is created, but the 4 should be, I see. So and is right. So for the second one can keep track of the cloned node. Okay, so when we get the original neighbor and cloned, we can get cloned neighbor, yeah. And the cloned neighbors must be initialized with empty list, so we can append cloned n is the node, so the node body cloned, yeah. And also we have to memos. It's redundant. I feel like redundant. But when we create these nodes, it should know about its parents, so this pair works for this. And there is a case where we want to create a node that is already created. So to avoid this, we want to introduce the memos, and if it's already created, we can skip it. Oh yeah, skip it. Yeah, that makes sense. And so memos 1 be cloned node, okay, and initialize the Q. Here is a base case, and Q have a original node and its parent. Original node and the cloned node that should be parents. So we get the node and parent node. Before creating new node, we want to check it. If that is already created, we don't need to do anything. Continue. And otherwise, we have to create new node, and we want to and parent neighbors append cloned. Okay, and at last and cloned. Yep. Is this correct? Two and four. So 1 should have 2 and 4 as neighbors. Yeah. This is assured because we put the node and the cloned node. So this points this, and this points 2 and 4, and 2, 4. That must be created at once. And at the time, the parent points this one, and these neighbors should be updated. Yeah. And that makes sense. And finally, non-type object is not callable. Node. Okay. Q has no length. Okay. empty. Takes long. Might be long. Long and wrong. I see. We didn't update memos. Okay. Wrong answer? 2, 4. Cannot append the 1. Cannot append the 1. I noticed I should code on this editor because for the interview mock I took today is like this, so we cannot access the IDE features on VS Code, so yeah, I should practice on this editor. So let me see. Node is created, append it, get from the queue, and if it's not none, we can get the node, and yep, if it's none, we can create a new node. That's a cloned node, okay? And update the memos, and we should update parent. Yeah. Yeah. Maybe time limit exceeded. The problem here is It's already appeared. We don't need to append the queue, right? If memo and value is none, we append it. Okay, because the one is already done, so yeah. And it should have adjacent list 2 and 4. That is assured because yeah. Oh, I see. This is not good. 3 is already initialized. But the node doesn't have a adjacent list because 3 is already created, so we cannot put 2 and 4. Yeah. 2 is already created, so the 3 cannot have 2 as a adjacent list in this implementation. That's a problem. Yeah. So maybe we have to visit all node, but we have to avoid the infinite loop. How about marking it as finished? For example, for 1, node should be created, and when we create 2 and 4, the node 1 is completed, because when this node is created, yeah, we can append them to the one's adjacent list. So yeah, we have to wait for 2 and 4. Okay. Oh wait, in order to check if the node is completed or not, we have to keep track of the original node's adjacent list. That's not efficient, I think. 1 is created, and we want to append 2 and 4. So node 2 is created, node 4 is created, and then like this, 4 and 2, it requires 1 and 3, so n3 is created. Okay, so let's create node at first, and then we update the node's adjacent list for each. Time complexity is not bad because that is not nested loop. Yeah, we can but how okay. So the step 1, initialize all node. Okay, neighbors is put we get cloned node like this. Memos index original dot value, and we have to for neighbors in original neighbors. Yeah, we can get the neighbor memos nb value. Okay, so clone neighbors append n. Okay, and complete it. Turns true. And then call next. Completed nv value. If not completed, we call it. Memos. How about this? Wrong answer. DFS. Okay. Not bad. The Q. Yeah. The Q is good. This is so simple DFS. All too new. Copy neighbors append DFS. But my solution is not bad because it's just 10 millisec difference, so I don't care about it. So first we handle the edge case. Step 1, initialize our node. Before updating their neighbors. We will use BFS. Node. Stores node to copy. Okay. Qget. If the node at the index is already created, we don't need to process it. Copy node and memo it and update the queue. Update the queue. Its neighbors is the nodes to be copied. we relation of neighbors have cycle that's why we have to keep track of this function completes to update the node's neighbors. And then do next. Let's clarify the problem first. We are given a reference to one node in a connected graph, and each node have a value and a list of neighbors. What we need to do is return a deep copy, basically a new graph, where all nodes and edges are cloned but structure stays the same. We will handle this in two steps. Clone all nodes first, so that difference exists. Then connect their neighbors. We will use BFS for cloning and DFS for linking. Step 1. Create all the nodes first without worrying about their neighbors yet. We'll do this with BFS so we can discover every node. Assuming node values are within 1 to 100. So yeah, multiply 1. Yeah, we prepare 101 non-elements. And BFS traversal, we go level by level through the original graph and make sure each node exists in our clone memory. If this node has already been created, we skip it. Otherwise, we make a new copy and we enqueue its neighbors to process later. Step 2. Now that all nodes exist, let's connect their neighbors. Since the graph may have cycles, we will track which nodes we've finished linking. This function updates one cloned node's neighbor list. Then continue recursively for any nodes not yet completed. Start DFS from the original starting. I'm wondering, my solution is okay, not bad. Yep. Okay. My solution is not bad. We are given a reference to one node in a connect graph. Each node has a value and a list of neighbors. What we need to do is to return a deep copy, basically a new graph, where all nodes and edges are cloned but structure stays the same. We will handle this in 2 steps. Clone all nodes first so that reference exists, and then connect their neighbors. We will use BFS for cloning and DFS for linking. Either is fine, whatever. Step 1. We'll do this with BFS so we can discover every node. Oh, okay. I will finish. Today is 20. And November 7, 8, 9, 30, 31, 1st, 2nd. Okay, 1, 2, 3, 4, 5, 6, 7, 8. I have 2 months, 8 weeks. So how many problems I can solve in 2 months? 2, 2, 2, 2. For weekdays, 2 problems per day. So 10 problems plus 10 problems, 10 problems to 20, 20, 20. So 20, 20. Total 200 because I've solved 60 already, 65. Hmm. 20 per week. 20 per week is not difficult. I want to take a mock interview. So yeah. Switch to system design. System design or wait. Hmm. 200 is over too much. So I want to let me see the current. Yeah, I already solved 160. So the total would be 200. So I will system design and fundamental knowledge, because I need to be able to explain how it works. So in Japanese I can do it, but in English I'm not sure. I'm not confident because I don't know the words and vocabularies, so I need practice. Yeah. So the system design and the basic knowledge, system foundation, operating systems and networking and stuff. Yep. Mock interview. Mock interview. Yeah, I transit from self-talk practice to mock interview. Yeah, interactive practice. Yeah, that's important. This is for coding field. I have to practice system design and foundational knowledge skills. I have to explain it. So system design. Foundation system. うんうん。December, December, December. Spell is correct. December. うん。I aim to apply a new position in December. That would be the first job interview in English. Yeah. So December, January, February, March. Yeah, I want to start to work at a new position from April. So, yep. December. Seems good. Seems good. Seems good. Seems good. Seems good. Mock interview. I will take mock interview tomorrow. Once or twice. Once or twice. Once. No. Solve 65. English conversations is important. System design and foundations. I will spend 3 weeks for this, and prepare job interview. Prepare for job interview. I will apply internal transfer. Start to apply. December, March. This is my plan. Yep. 2020. Maybe I can too. Yeah. And for this week, I want to organize the English phrases and sentences. For efficient mock interviews. Yeah. So we already 65. We can reduce this 15. Focus on more conversational, interactive English. Yeah. Okay. Thank you for watching.